These are the answers to the practice test in statistics. First of all, some data about the heights of two groups of people. Estimate the mean of each group. Well, we're going to ignore the cumulative frequency column for the moment. That's for later. And then let's look at these numbers. So we've got the first group, heights between 150 and 160. The people in that group could be anywhere in that range, and we're going to make the assumption that they're all in the middle, 155. And then we're doing that for all the groups. We're taking the midpoint of each group and assuming everyone to be at that point. So in the first line, there's two people that we're assuming to be 155 centimeters tall. So that makes a total of 310 centimeters. 2 times 155, 310. Same for the other groups. Four people that we're assuming to be 165 centimeters. 4 times 165 makes 660. So if we work all of those out and add them all up, we get the total assumed height of all the people, which comes to 3545. So if there's 20 people and they have a height in total of 3545, then the average is the total height divided by the total, I should say the total number of people, that's a misprint, 3545 divided by 20, so we're estimating the mean is 177.25. Question 2, what is the modal category of each group? Well, the modal category is the one with most in, and in this case it's 170 to 180 because that's got 6 people in it, more than any other group. Question 3, the median category of each group. Well, the median is the middle person if you put them all in order. So we need to think about which people are in each group. So the first group has 2 people in it, so that's got person 1 to person 2. Because that group ended with person 2, the next group's got to start with person 3, and then it's got 4 people in it. So the last group ended with person number 2, so 2 plus 4 is 6. The next group ends with person number 6. That means that the next group's got to start with person number 7, and it's got 6 people in it, so the previous end of 6 plus an extra 6 makes 12. And then the next group's got to start with person 13, and then it's got 5 people in it, so the previous end of 12 plus an extra 5 means that group ends with person number 17, and so on. And then you should get the last group, person number 20 to person number 20, because it's one person on its own, and then the whole thing adds up to 20 because there's 20 people. Now the median person out of 20 people is person number 10.5. You get that from 20, add 1 divided by 2. But that doesn't mean that 10.5 is the median. The median is the median category is the category that's got that middle person in it. And you can see that person number 10.5 would be in the 7 to 12 category. So the median category is 170 to 180. Question 4. Make a cumulative frequency graph for each group and estimate the median and quartiles. So we're just using that last column now, and the cumulative frequency is the total so far. So 2 so far for the first group, plus an extra 4 makes 6, plus an extra 6 makes 12, plus an extra 5 makes 17, plus 2 makes 19, and plus 1 makes 20. Of course we get to 20 because there's 20 people. So I've done that for both groups of people. And then for the cumulative frequency graph, we plot the end of each category against the cumulative frequency. So we're plotting 162 to show that there are 2 people whose height is up to 160, 176 to show that there are 6 people whose height is up to 170, 180, 12 to show that there are 12 people whose height is up to 180, and so on for all the groups. And then one more thing we should plot is the start of the first category against 0. So in this case 150, 0, showing that there are no people below 150. So I've done that for the other set as well. And then the cumulative frequency curve for the first group looks like that. So a nice smooth curve through all the points. And then we can estimate the median and the quartiles from that. So the median is the 10.5th value. So if you read along from person number 10.5 and down, that comes out to be 178 on my curve at least. And then the quartiles are the people 1/4 and 3/4 of the way along the group. So out of 20 people, 1/4 of 20 is 5. So the 5th person has a height of 169 centimeters, and then 3/4 of 15, 3/4 of 20 is 15. So the 15th person has a height of 185. So the median and the upper and lower quartiles are 169, 178, 185. Those are the 3 values that split the data into 4 equal groups of people. I did the same for the other group and I got 164, 173, 182. And then for question 5, I put those on box plots. So you've got group 1 and group 2 represented by a box and a whisker. The whisker shows the full range of the data, the lowest to the highest values, and then the box shows the lower quartile, the median with a line, and the upper quartile at the top of the box. So I've got 2 separate box and whiskers for the 2 groups, and then I've got the heights labelled on a scale. I should have put a label that said height in centimeters there, and that 0 shouldn't be there at all. That's just because I copy pasted it from the cumulative frequency curve. So in a box and whisker plot question, you are typically trying to compare 2 different groups of data on a comparable quality. So in this case, height. And you're looking for 2 things. You're looking for the general central tendency of the data. So in this case, group 1 is slightly taller than group 2, and you can see that from the median, for example. And then the other thing you're looking at is the range of the data, so how spread out the 2 groups are. So a good answer to a question with a box and whisker always involves the central location of the data, which group's bigger, and the spread. So I've made a comment in plain English and then a statistical comparison, the median. And then I've made a comment in plain English that the range is, well, greater, or the values are more spread out, I might say. And then you can talk about the interquartile range or the range. The interquartile range is more useful because the range is just skewed by the upper and lower value if they're particularly high and low, whereas the interquartile range involves more of the data. So the interquartile range is a better spread, a better measure of the general spread of the data. And the interquartile range is the upper quartile minus the lower quartile. So for group 1, that's 185 minus 169, which is 17. And for group 2, the interquartile range is 182 minus 164, which is 18. Yeah, so to recap, I'm not sure I said that right before. 185 minus 169, 16. 182 minus 164, 18. So the interquartile range is slightly greater for group 2, 18 compared to 16. Group 7, data about the math scores of 20 people. What is the mean score? So that's just adding them all up and dividing by 20 people. 67.9. So just adding these straight up. What is the median score? The median score is the one that's in the middle, the 10.5th value, as I said before. They need to be in order, so it's the 10.5th value in order. So if I put the values in order, there they are. And then 10.5 is kind of between the 10th and the 11th value, which are 65 and 69. So we take the median to be the mean average of those, 67. And you can see at that point where I've put the arrow, it's right in the middle because you've got 10 values above it and 10 values below it. The modal score is the one that there's most of. In this case, it's bimodal. There's two modes, 89 and 100. Which of the above three types of average best represents the data? Well, let's look back on them. The mode being 89 or 100 doesn't really say much about the data set as a whole, so that's not telling us much. The median and the mean, which are both quite close to each other, 67.9 and 67, they're telling us a lot more about the typical person in that set of data. So the median or the mean, for that reason, are better than the mode. Represent the data on a scatter diagram. So I've got the hours spent revising and the score. So each line of this is a single person. So the person who spent 4 hours revising got a score of 53, for example. So plotting all those on the scatter graph, we get that, and we are observing positive correlation. As the scores increase, or so as the hours revising increase, so the score increases. By the way, I've put the hours revising on the horizontal axis and the score on the vertical axis because the score depends on the hours you revise, and you tend to put the dependent variable on the vertical axis. Then it's the rank correlation coefficient next. So we're calculating this thing that's measuring how well things are correlated together, how well the hours spent revising and the test score are related to each other. So I'm ranking them all now. So the most anyone spent revising is 9 hours, so that's first equal. Because they're occupying first and second place, I'm going to designate them both as 1.5 because it's the average, the mean average of the 1 and the 2, the places they occupy. Next we've got third place after 1 and 2, and we've got 3 things in third place. So they're really occupying places number 3, 4 and 5. So the average of 3, 4 and 5 is 4. So I'm going to designate them all as rank 4. Now we're up to 6th place, and there's just one that's in 6th place, so that's straightforward. And we carry on ranking them like that, and this is what we get. We do the same thing for the scores that people got, and then we're looking at the difference between those two ranks. So sometimes it's plus, sometimes it's minus, depending on whether the hours are ranked higher or the score is ranked higher. So this is just a straightforward subtraction. 20 minus 20 is 0. 15.5 minus 17 is minus 1.5. 18.5 minus 19 is minus 0.5, and so on. Then we're taking those numbers and squaring them to get that. And then the total of those squares comes to 90.5. So then we start to plug that into the formula. It says 1 minus 6 sigma d squared. So the sigma d squared just means the sum of, sigma means sum of the d squareds. So the sum of the d squareds is 90.5. So I plug 90.5 into the formula there. And the n is just the number of people, which is 20 in this case. So 20 times 20 squared minus 1. And it all comes out to be 0.932. Now, a correlation coefficient should always be between 1 and minus 1. If it's 1, then the data are very strongly positively correlated, and that ties in with our scatter graph back there that showed good positive correlation. If it comes to be minus 1, then they're very strongly negatively correlated. And then if it comes out to be around 0, well, then there's no real relationship between the two things, and they're not very well correlated at all. So score of near 1, good positive correlation. Minus 1, good negative correlation. 0, no correlation at all. No relationship between the two variables. Draw a line of best fit and use it to predict the score of someone who worked for 3 hours. So there's my line of best fit. I've put it going through this point here, which is the average of the two things. So the average person spent just under 5.5 hours revising and scored around 67. So I worked out the mean averages of those. The line of best fit should go through that point. It doesn't have to go through 0, and that's a mistake a lot of people make. But you can just plot that mean point and then kind of fit the rest by eye, although there are mathematical methods for working out the best line of best fit that you will encounter later. So someone who spent 3 hours revising, reading up to the line from 3 hours and across, we could predict that they'd get a score of 45%.